Fleming, and he was speaking about the physical constant and properties of self-regulating quantum fields.
Yes, for those who I haven't talked to yet, I'm a retired physicist who worked in industry, and now I work on doing basic physics research. I primarily focus on understanding elementary quantum field theory, as I call it, which is basically the particle pair model of space. I don't get into wave equations too much because wave equations without a physical medium are meaningless to me. You have to find a way to combine them. So I start with the physical medium and figure out where to go. The topic for this lecture came about when I was writing my book, God Hates Science. I decided to take on the misinformation that the fine structure constant and all the other physical constants are fine-tunable by some fine-tunement, which I think is nonsense. I think all the physical constants arrive from something physically real. And so that's what this lecture is about. Okay. First, here's a list of evidence that there is a quantum field. There's been quantum field theory deniers for the last century that have dominated what's taught in physics. But it's a pretty substantial list when you go through it. And to me, the most important is the Casimir effect. And I have a little graphic here. If you're not familiar with the Casimir effect, Casimir and Polder came out with a paper in 1948, and they came out with a two-plate example. And if you have two plates in space, some of the quantum fluctuations that have too long a wavelength or destructively interfere can't exist within that region of space. And Casimir came up with the idea that the quantum fluctuations interact by van der Waals forces, like they're charged dipoles, and that they push on the plates. And so he thought within the Casimir cavity, if they're close enough, the plates will be pushed together. It took almost 50 years before it was experimentally confirmed. And so that means that space behaves like it's charged dipoles that participate in van der Waals forces. And since then, they've been using this in nanotechnology, and they treat the charged dipoles as Dirac-Fermion particles, which prototypically are electron-positron pairs. But hypothetically, they can be any Dirac-Fermion. Now, here's some other theories that are out there that haven't been proven. Hawking radiation was interesting to me because that was the first time when I was a youngster that I heard about the particle pair model. And for a lot of people, that's what they first hear about. Now, during Dr. Unziker's presentation, he mentioned Robert Dicke. And in Dicke's paper on gravitation, he started out in the introduction by saying that one of the great things about understanding space as a polarizable medium, in addition to the electric and magnetic fields being a real field that's propagating through a real material substance, is the fundamental constants, permittivity and permeability, fall out automatically as features of the field. Now, we can think of both of those as the field's resistance to polarization and magnetization, but then we have to figure out why there's resistance. And the reason why is quantum van der Waals torque. Anytime you have a field that participates in van der Waals forces, there also will be van der Waals torque. Now, this is something that's people work on in electrochemistry, but it seldom comes up in physics. In fact, I'm the only one I've ever seen who's working in quantum van der Waals torque and its effect. But basically, the van der Waals torque is, you can think of it like inertia, except this is the origin of inertia. That the dipoles in space don't want to move, and it takes energy to make them move. So anytime you have a body moving through space, it requires energy to make those dipoles rotate. And so since we have the permittivity and permeability constants arising naturally out of the quantum field, that means that the speed of light is a tertiary constant. That the quantum van der Waals torque is first, permittivity and permeability next, the speed of light third. Now I will say that as part of Dickey's paper, he took a Machian view to how the permittivity and permeability constants arose. And a lot of the work that has been continued based on his work from 1957 has been based on a Machian approach. But what I say is, basically you can think of the quantum energy in this controller in my hand is greater than all the mass energy in the entire visible universe by a factor of 10 to the 48, at least. That's assuming the Planck cutoff. So we first have to figure the quantum field effects and what's going on there. And my claim is that the quantum van der Waals torque is what determines the permeability and permeability of free space. And the Machian term is just a refinement of that. Okay, so when we think about relativity, I first want to point out that in space, a literary definition is it's a boundless region that contains matter, where space itself is not matter. And so a non-material space can't have physical dimensions and it can't have physical clocks, which means that all of Einstein's relativity theory is based on fictitious rulers and clocks. And so you start with fictitious rulers and clocks, and you can never derive a theory that's not fictitious throughout. So how do we fix that? Well, if we want to combine quantum field theory and general relativity, which is the goal, then we have to pick one set of physical rulers and clocks. Now, it turns out we have wavelengths and frequencies in the quantum field. That every single quantum fluctuation has a wavelength and a frequency, which means it has physical dimensions and it has clocks that has time. And so that's where the physical dimensions, the physical clocks and time come from. And they're regulated by the van der Waals torque. Now we also have to consider that when we have a quantum field, we have a rest frame. So any version of relativity that is frameless is not true. And we actually know the rest frame from CMB, cosmic microwave background measurements. It's a physical impossibility for there to be two separate rest frames, and we've already measured one. And in particular, the CMB is blackbody radiation. The distribution follows a blackbody curve. And blackbody radiation in a vacuum involves an interaction with a quantum fluctuation with the material at temperature. And then the quantum fluctuation gets some of that thermal temperature and it can no longer annihilate, so it becomes a photon. So what changes the van der Waals torque? Well, if you're moving relative to the rest frame at a velocity, that gives you an apparent increase in van der Waals torque. If you're accelerating, that gives you an increase in van der Waals torque. If you're near a physical body of stable matter, electrons, protons, neutrons, that increases van der Waals torque. But if you have a Casimir cavity, that decreases the van der Waals torque. And on the second slide, I showed the Scharnhorst effect, which is the idea that within a Casimir cavity, the speed of light could be greater than it is in free space. And that's for this reason. So we have an effect where the van der Waals torque is what changes the clock rates. That an observer moving relative to the rest frame experiences a clock rate slowing, and that's been measured in GPS clocks in orbit at different velocities. And so we have to account for it. And it also accounts for redshifting when you have experience a change in gravitational potential because you're further away from a body of matter. Now, as for the speed of light, when you change the constants, permittivity and permeability, you change the speed of light. It's that simple. And if you change the permittivity, you end up with a ratio of permittivity, so you get a dielectric constant. So you can think of it in terms of dielectric constant, which is how Dickey developed his model, and then Puthoff did a similar development in the 90s. Now, the van der Waals torque also affects how far you travel in a given time, so the distance and time change at the same rate. So it makes it appear like the velocity is the same, even though both distance and time have changed. At this point, I'll say that I haven't done a full development of special relativity in this thought experiment. So if you have detailed questions about that, I haven't worked through all the possibilities. Another key point is that photons, since they produce an electric and magnetic field, and an electric and magnetic field propagates through the quantum field rest frame, that means that as far as the photon is concerned, it's traveling through the rest frame. It's not traveling at the speed of the source or the speed of the detector. Once it leaves the source, there's an energy shift, but the photon behaves like it's traveling in the rest frame. And the whole idea that a photon travels with the velocity of the source is part of a whole bunch of the contradictions in the theory of relativity. And then as far as space dimensions, the quantum field sets the spatial dimensions. It's the wavelengths of the quantum field in the rest frame that determine the dimensions of space. And like I said, those can be modified locally depending on the distribution of matter relative to that point of space. But a moving observer doesn't change what's happening in the quantum field in the rest frame. That observer is just experiencing an increase in torque. They're not producing length changes. You can't have a million observers moving a million different velocities, causing a million different length changes in a million different directions, all simultaneously. It's impossible. So we don't have length contraction, and we don't have space curvature. Both of these are mythological. And another point, in 1907, Einstein published that if you apply a clock rate correction to the Michelson-Morley experiment, you get a correct result the same way you do if you do a length correction. But you can't do them simultaneously or you get the wrong result. And so Einstein felt that the clock rate correction was correct and the Lorentz correction was wrong. But then he turned around and said, but my theory's right. So then we have the deflection of light. And similarly, Einstein, as Unzicker pointed out in 1911, he derived that you can get a 2gm over RC squared term just from a variable speed of light measurement. And this is basically a change in the dielectric constant. But then in 2015, he did the variable clock rate and space curvature correction to get the 4gm over RC squared term. And the thing is, you can't do all three terms or you get the wrong answer. So one of these is wrong. That one's wrong. Einstein made a bad decision there. So what we have is, instead of general relativity in Einstein's development, we have general relativity in a quantum field development using the quantum field clocks and rulers. But that makes it an electromagnetic phenomenon because the quantum field is an electromagnetic phenomenon. So general relativity doesn't have anything to do with gravity, it never did. It's strictly electromagnetic, and it's due to the van der Waals torque, which causes clock slowing and changes in permittivity, permeability, and the speed of light. So with quantum general relativity, we have an electromagnetic effect. It's in flat space with variable clock rates and variable speed of light. And this type of general relativity, variable clock rate, variable speed of light in flat space has been developed by numerous physicists, and it's been shown that you can construct this in a way that is equivalent to general relativity. And all the proofs of general relativity can be explained. However, there's other problems that need to be solved. Namely, acceleration. Newton and Einstein never explained how you get acceleration from bodies of matter. And it's not explained in electromagnetic forces except for the Casimir effect. So what happens in space, and I'll try to illustrate with some magnets first, is if you think about how magnets react, whether they're attractive or they're repelling, neither of these have jetpacks, and they don't lose mass when they're accelerated, so there's no propulsion system involved. They're being pushed. They're being pushed by the quantum field. And the dynamics of it are exactly the same as the Casimir effect. You're looking at differentials of quantum field pressure, where in the case where you have opposite charges or opposite poles of a magnet, the pressure in between is reduced relative to the pressure pushing them together. And then in the opposite case, when you have like charges, the pressure pushing them apart increases, or like magnetic poles. And so you can think of electromagnetic acceleration as an extended Casimir effect. The one key part of this is that you have to have a pressure force that varies with the inverse square of the distance. And Puthoff tried to develop an argument for this, and it wasn't really convincing. I've been working on a different approach because in space, I see two basic types of Dirac fermions. One is electron light and one is proton light. You have positive matter and charge on one end with its proton light versus negative matter and charge on the other end. While electron is negative charge and positive matter, while on the opposite end for the positron, it's positive charge and negative matter. And those dipoles together will always oppose each other whichever way they line up. You can think of it when an electron and positron together, there's a 780 keV potential that prevents an electron from merely falling into a positron. And that potential is involved with a constant state of repulsion. There's another more general way to think about it, but I'll get to that. But that's an area where I need to do a mathematical derivation of it to make it more bulletproof. So what happens if you have an electromagnetic acceleration effect where bodies are being pushed from this side and in between, you get a shadowing effect, as Fadia and Lesage proposed long ago, but it's electromagnetic. The force pushing on the bodies is purely electromagnetic, but you can still have neutral bodies that are shadowing this electromagnetic pressure force that develops by the quantum field. And so in that way, you have an acceleration that looks like an acceleration of bodies due to gravity, but it's strictly an electromagnetic phenomenon. Now, another area where there were developmental problems in physics is people haven't come up with an appropriate physical description of inertia, although some people here have been working on it. When you look at inertia, you end up, no matter how you look at it, you end up with something that looks like self-induction. You have a body moves, something rotates, and that rotating thing causes the body to keep moving. And so it ends up looking like an electromagnetic force, like a Maxwell force or a Weber force. And no matter how you go about it, you end up with something that looks like electromagnetism. And Heaviside really figured this out in 1893, and hundreds of physicists and many in this room have come to the same conclusion, that there's some sort of electromagnetic-like force that works with electrically neutral bodies. But one of the key secrets here is that the speed of light's the same. And so permittivity and permeability, the magnitude of that has to be the same in order for this electromagnetic-like force to work out. Now, what I proposed 20 years ago is what I call the matter force, because I think that there are several mistakes in the way Heaviside and others have approached this. I think that it's not mass, because there's no negative mass. I think it's matter, and any matter is a dipole. And I first came to that conclusion just because if you look at electron and positron, there's no other dipole property. But you can think of it in terms to the solutions of Dirac equation. Dirac showed that his two solutions, one was a negative rest mass and then a positive rest mass. Well, what in the world does negative rest mass mean? But you can say that a negative rest mass is equivalent to negative frequency, negative time, which correlates with the time inversion we know with the electron moving forward in time looks like a positron moving backwards in time. And at the same time, it may be the hint that it's really a dipole-like property, and that we should have been looking at matter as the dipole all along. And then the other part of it is that we always assume that we have a linear force that must equal gravity, that must be attractive instead of repulsive. Well, now we know that there's a force causing matter to move away from matter that's responsible for the accelerating expansion of the universe. So we have to have a theory where matter is accelerating away from matter. So why should we mess with the direction of this? We already have an attractive force in the Casimir effect. So we can go ahead and say we have another force that's an expanding force. And then gravity is the summation of the two forces and other force components of this matter force. So we can develop this force and basically come up with a table where we have electrically neutral and electrically charged terms that are all the same. Now, one thing to point out is every electrically charged body is also matter. So this matter force, the neutral matter force, is embedded in the electromagnetic force. It's part of it. When we deal with electromagnetic forces, we deal with both of them simultaneously, most of the time. So developing them, it's not necessary to develop them separately. It's only necessary to combine them. So we can come up with the Maxwell force equations that I showed here in basic terms. Nothing fancy. Now the thing we get if we have a neutral matter force is it explains inertia, it's self-induction. It explains the interaction of spinning tops and gyroscopes with the quantum field. You can explain the perihelion of Mercury as an effect due to the rotation of the sun. Tidal forces, solar and Earth dynamos, spiral galaxy formation. You end up, if you have a Lorentz type force, that explains how these arms are able to hold in. And there's been work on people simulating spiral galaxy development using electromagnetic field equations, and they're able to develop spiral galaxy formations quite easily if you include the Lorentz force. So Lorentz forces can account for dark matter, and then as I said, repulsion between matter can account for dark matter. But what that means is that in the electromagnetic theory of gravity that the constant G is a summation of the Casimir effect is attractive, the Lorentz forces, which are attractive, and the matter force, which is repulsive. And so G's not really a constant. I have a test I want to do on the Lorentz force theory because there's an anomaly where the mass density of Saturn is half that of Jupiter, which doesn't make any sense that two gas giants would have vastly different density. But the velocity of Saturn is nearly half that of Jupiter, and it's nearly twice as far away. So the Lorentz force would be significantly smaller. So it could be that this anomaly in the mass density is strictly a miscalculation. So we could, if someone likes tensor algebra, they can combine Maxwell stress energy tensor in a quantum field space-time metric, which is flat space with variable time, and you can get an equation like this that explains all 5 forces, including mechanical forces. And I include the strong force in here because another calculation I did long back, if you treat the proton and neutron as a body that interacts by Casimir effects, which it must do because it's able to scatter, so it must interact by Casimir effect, and you use a force proximity approximation for 2 spheres, you find out that the attractive force gets much stronger than the Coulomb repulsion. And the distance in femtometers is almost identical with the range of the strong force. So we can explain the strong force completely as a Casimir effect and not need to do other theories. Now the proximity force approximation just measures the effect between the inner surfaces. It doesn't measure the effect between the outer surfaces. So I need to go back and do a complete integration of the entire surfaces of the entire Casimir effect. And also it has somewhat of a Fabio type effect on top of it. So in order to get a final version of this, it needs a little refinement. And then weak interactions can also be explained by quantum field effects. I mean, you could say that we could use the existing theory of weak interactions. But if you consider what an electron and positron pair can do, it can interact with a proton, and the electron-positron pair allows it to jump that 780 keV potential in order to produce a neutron. And then a neutron can decay to a proton. So you can explain the entirety of beta decay functions as quantum field effect interactions. You can also explain particle exchange theory within a nucleus, where a proton gets converted to a neutron and vice versa, using the same type of interaction. And I also included here as an extra the spontaneous emission can be explained as a quantum field interaction, and even quantum jumping, where you can have an interaction that causes an electron to appear to jump from one position to another, and it's actually a new electron. And this will appear to violate the speed of light. And so overall, and you can look at Feynman diagrams, and any wiggling line you find that is an interaction of some sort mediated by something, you can explain it as a mediated interaction due to quantum field effects. Now moving on to the other constants. With electric charge, I was looking at the this version of Gauss law and trying to figure out how I could explain it as a quantum field effect. And I realized that the flux of polarization is regulated by the torque of the quantum field. And so that made me realize that we've been looking at it backwards. The charge, the electron doesn't have a magnitude of charge. The magnitude of charge is determined by the flux in the field. the particle itself only acts like a simple polarizer. So it polarizes the field, and then we end up with charge based on the quantum field effect. So we've had it backwards all along. At least, I mean, that's what I'm thinking. So that means that there would be no fractional charges in free space. You could have fractional charges in a Casimir cavity, such as with the fractional quantum Hall effect. Now, as for Planck's constant, which I'll get back to, I like to just set it to 1 in natural units, which to me is interesting that energy equals frequency, or energy is the inverse of time. And then, in that case, you can look at the total energy as a sum of frequencies, or this is the energy density equation for the quantum field, which also it takes into account a range of frequencies. Now, as for the fine structure constant, with that, you can also, to get a better picture, put it in natural units where h equals 1. A lot of people do h bar equals 1, but if you consider h equals 1 instead, you get this simplified term. Fine structure constant is electric charge squared over 2, which looks like the log of x. So we can think of the fine structure constant as being the volumetric integral of the flux of polarization. And then if you want to reintroduce the constants in front, you can. So I really think, because this is based on the most fundamental equation of the fine structure constant, that it's the most fundamental description of the fine structure constant as the volumetric polarization of space. Now, next, I need to tackle spin. And normally we think of the polarization of space not inducing any rotation. That's the standard idea, that when an electromagnetic field forms, it doesn't cause rotation. But I think that's wrong. And my argument is if you take two dipoles that are partially oriented but need to rotate a little bit more, you end up with like charges moving together one way or the other, or one of them needs to move the center of mass of the quantum fluctuation. And so that requires energy. What requires less energy is if the dipoles all rotate the same way when they're being polarized. And we need to keep in mind that there's many orders of magnitude more dipoles in space than are necessary for an electric field to form. So only a few dipoles need to rotate. So nature can select the ones that are close to what it needs and just rotate those. So in this case, it appears to me that spin is a quantum field effect. That the actual bare particle in the middle that's polarizing doesn't have to rotate at all for there to be a rotating field around the particle. And this also helps explain how you have similar or identical spins for multiple particles of different dimensions. So you end up with the same angular momentum. If the angular momentum is due to the quantum field, that simplifies things. So as far as spin and angular momentum go, you can describe it by this equation, and this also has Planck's constant in it. All of these terms I've already discussed so far are functions of the quantum van der Waals torque of the quantum field, and they arise naturally. So the spin, angular momentum, and Planck's constant also must arise as a quantum field effect. Now, next I tackled the electromagnetic moment. Now, if we classically are computing a magnetic moment, we need charge, we need a radius, and we need an angular velocity. Well, here we have mass in the traditional version they put in the textbooks. So what's going on? Well, what's going on is mass is really telling us we're using the Compton wavelength. So the actual equation is this. we're using charge, the Compton wavelength as the effective radius, and the speed of light as the velocity. And Planck's constant drops out. And the reason that the G is 2 instead of 1 is because we have dipoles. Because with dipoles, if you think of it in terms of a spherical shell model, you have two spherical shells nested together, rotating in opposite directions with opposite charge. So each one contributes a factor of roughly 1, so you get a G factor of 2. Initially, when people were using the spherical shell model, they expected it to be a factor of 1 because they were only using a single shell, not realizing that space was filled with dipoles. And note the distance factor and the speed of light. The speed of light, of course, is going to be a limiting speed for this rotating sphere of quantum fluctuations, because it just can't exceed that. Now, if we consider the proton, we have a similar problem. We have mass in here. Why is mass doing there? But fixing the problem is not as simple, because the Compton wavelength for a proton is different from the actual charge radius of the proton. So the physical dimensions of the proton are different. And so if we use the Compton wavelength, we get the wrong result by a factor of 1.3245, which causes us to have a G factor that's off by a similar factor. So if you actually redo this, come up with a proton radius magneton, then you get a G factor of 2.1, and you can, I'll state that if you take the correction factor to the G factor for the electron and multiply it by the square root of 1836, you get 0.1. So I'm convinced that you can account for this as a self-energy of the proton issue. So once again, we can place it in terms of charge, a wavelength, and the speed of light. Noting this time, the wavelength is much smaller, but the speed of light is the same, which tells us that the proton's rotating faster. Now, moving on to mass. Mass has been shown to be electromagnetic long ago, and to me, if I put it in natural units where mass equals frequency times permittivity and permeability, it makes it pretty obvious that it's electromagnetic. So of course gravity should be electromagnetic too. Now we have Dirac, when he was dealing with his positive and negative MC squared solution to his equation, he was trying to figure out why both the proton and electron had positive mass and why there's no negative mass in reality. He came up with the idea that the particles have to push against the quantum field, and the energy of the particle pushing against the quantum field was where it got its mass. Now, I've looked through Dirac's papers, and I never saw him actually try to calculate this. And that was in a speculative paper back in 1930, when he first speculated that the positive solution was a proton, not a positron, but he got credit for particularly the positron anyway. But if you actually calculate it for a proton, using the charge radius and using the mass energy density equation for the quantum field, it turns out that the amount of energy displaced by a shell the size of a proton is equal to the mass of the proton. So we can consider mass to be just displaced quantum field energy. And we can do the same thing with the electron, but in this case, it's the Compton radius again. Okay. So all of the electron and proton properties can be determined based on the quantum field, except for the charge and whether it's matter and antimatter. And so both behave like a bare particle that's a polarizer surrounded by a quantum field. And the quantum field itself would be bare polarizer, and which is why they're massless, because they don't have time to develop a quantum field around them. And we also have matter and antimatter polarity. If each of these particles, proton polarizers tend to be surrounded by proton-antiproton pairs. Electrons tend to be surrounded by electron and positron pairs, which gives a different polarization, which gives them a different size. Now, as for other physical constants, all of these constants are functions of constants that are previously mentioned. So they too will be quantum field effects, although I haven't had time to step through all of them. And here's some more constants that are also derived from constants I've already covered. So we have all the physical constants can be derived using this mechanism as quantum field effects, as well as all the forces can be unified using this approach. And this approach also gives a basic model for the electron and proton. So I included references to my papers and other papers I've referenced. And here's my email here, no initial. If you shoot me an email, I'd be happy to send you a copy of the presentation or a copy of the papers. And here's a couple of my books if you're interested in those.
Okay, thanks a lot.